All right, good morning. This is Ms. Cater for Monday morning, first period pre-AP physical science class. We're going to talk about notes 7.4 and 7.5. So since I'm trying to do two in one, I'm going to have to talk kind of quickly today. We'll skip over some things, so please make sure that you read these notes carefully on your own. And if you have any questions, make sure you let me know on Tuesday. Okay, first off, Newton's three laws. We've talked about some of these a little bit, especially the first and the second. So Newton's first law is the law of inertia, which says that an object at rest will remain at rest until it's acted upon by a force, a greater unbalanced force. An object in motion will continue in that same motion with the same speed, same direction, same everything, unless something else acts on it. So an example would be why you wear your seatbelt in your car. If your car hits another car, while you're at rest, you'll go flying into the opposite side of the car. If you hit a car, you'll propel it forward as your body is in motion as well. Even if you're seated, you're still, as far as the car is concerned, you're still in motion. And you will keep going in that motion. And so you'll go flying out of the car. So Newton's second law, this law says acceleration is produced by a force when a force acts on a mass. So if you have an object and you apply a force to it, then that object will have acceleration. The greater the mass of the object, the greater the amount of force needed to accelerate that object. The more force you have, the faster you will move. And here's the equation for it. Force equals mass times acceleration. How much force do you think it would require to move your desk? And then think about how much force it might require to move my desk. Okay, or if you had a regular student desk versus moving my desk. So that's Newton's second law. The amount of acceleration something has depends on its force and its mass. The force you apply and its mass. All right, Newton's third law. For every action, there is an equal and opposite reaction. This one we have not talked about before, but you experience it all the time. A good example of Newton's third law is launching a rocket. The Earth is providing resistance to the rocket moving forward, so the rocket fires its engines. The blast from those engines pushes against the Earth. Okay, so it's pushing down, which then causes the rocket to move forward. So for every action, there is an equal and opposite reaction. The engines push on the ground, and then that causes the rocket to go up. And that is Newton's three laws. Law of inertia, law of acceleration, law of for every action there's an equal and opposite reaction. All right, next page, when talking about this, so 7.4 was just one page, listing Newton's three laws. Make sure you know those. Make sure you know the equation for Newton's second law. And that brings us to 7.5, momentum and collisions. Before we can talk about these, we need to talk about the difference between vector quantities and scalar quantities. Okay? Vector means that something has a direction with it. So quantities that have both a magnitude, which is a number, and a direction are vector quantities. So velocity would be an example. Velocity is a vector quantity because you have a magnitude, say 50 miles per hour, and then you have a direction, north. That makes it a vector quantity. They can be positive, meaning that you move forward or upward. They can be negative, meaning that you move backwards. Remember when we did our velocity position versus time graphs, we had a graph where the line sloped down. It had a negative slope. That meant that the object went in the opposite direction. Vectors are always drawn using arrows. Okay. So for example, a train is moving north at 550 miles per hour. This is a vector quantity, and we would draw an arrow, and we would put 550 mph north, and that lets you know it has a magnitude and a direction, then it is a vector. Scalar quantity, on the other hand, is just a number. There is no direction. They also can be positive or negative, but there is no direction associated with a scalar quantity. Saying that a cheetah can run 70 miles an hour is a scalar quantity because you told how fast it's going, but you didn't tell what the direction was. Speed is a scalar quantity. Momentum. Momentum refers to the quantity of motion within an object. It is the product of mass times velocity. There are two types of momentum that we're going to talk about. Linear, which of course means straight line. So this is when an object is moving in a straight line. It has linear momentum. We can calculate it by multiplying your mass times your velocity. Okay? It's measured in newtons. Mass times velocity gives us newtons. So momentum is measured in newtons. I'm not sure why there's an S on there. There shouldn't be. Linear momentum observes the law of conservation of momentum, which says that in a closed system, momentum is conserved. And that goes back and relates to Newton's second law. The force applied equals to mass times acceleration. In a closed system, that momentum gets conserved. And when we say closed system, we mean something like a lab or in a vacuum or in outer space, where there's no resistance present, or when there's nothing from the outside acting on that thing. That is known as a closed system. The second type of momentum we have is angular momentum or rotational momentum, and this has to do with something that follows a circular path or a circular orbit. It is highly influenced by mass, speed, and the shape of the orbit. All things in angular momentum have an axis of symmetry. It means they have an axis about which they rotate. That is their axis of symmetry. Just think about tires on an axle. If you put a tire and attach an axle to it, well, the axle will rotate, which causes the tire to move in a circular motion. The tire is attached to the axle, the tire rotates around the axle. The way we determine the amount of angular momentum something has is using this formula, where L is the angular momentum, R is the radius, and mass and velocity are also incorporated in there. Angular momentum is measured in Newton meters. Angular momentum is measured in Newton meters. Okay. All right, collisions. Collisions are two objects running into each other, and we look at how those collisions can affect the momentum of the object. Energy in the form of a momentum can be transferred between two objects. Mass and velocity are very important in determining how that energy or momentum gets transferred. And this basically kind of centers around Newton's third law, that for every action, there is an equal and opposite reaction. Two types of collisions that we can have. We can have elastic collisions, and it's important to remember that in elastic collision, energy is conserved, but it is transferred from one object to the next. So if we think of two billiard balls, okay, when you hit the billiard ball, one will be set in motion, and that will it will collide with the second one, which will cause the second one to be put into motion. So all of the energy of this one gets transferred to the energy of the second one. So energy is transferred. Okay. All right. Momentum is calculated by adding the momentum of the two objects together. As long as it's an elastic collision, All you have to do is add the momentum of the first object and the momentum of the second object to get the total. If the collision is linear, the objects are always going to move in a straight line. If the collision is at an angle, then both objects will go off in different directions. So if we go back to our pool balls again, okay, if they're colliding along a straight line, then they're just going to keep moving in that straight line. But if you have one, that hits at an angle, it may send one of them off in one direction, another one off in another direction. So if they collide at an angle, then both objects will move away in different and opposite directions. Inelastic collisions are the second type of collision, and this is where kinetic energy is lost due to heat, sound, or destruction of shape. Please remember, when we say lost, we just mean that it's not usable. It has not been destroyed, it's just not usable. So an example of an inelastic collision is when two cars collide and they wind up sticking together. Okay, there's a loss of kinetic energy for both cars, but both cars eventually stop. The one moving faster keeps going, where the slower one stops immediately. All the energy is transferred to sound energy, heat energy, and the destruction of the cars. Okay. Another example, moving car, bug hits the windshield, the bug splatters. The larger car keeps moving, and the bug has lost all of its kinetic energy. It's just splat on the windshield, it's not going anywhere. But the bigger object keeps on moving. Inelastic collisions tend to leave the greater force still moving and the lesser force not moving at all after the collision happens. Let's look at a couple of these slides from the PowerPoints for 7. Hopefully that'll make this a little more obvious to you. Here's an example of a vector quantity. It is drawn as an arrow. It has both magnitude and direction. The top of the arrow is known as the head. The end of the arrow there, where nothing is written, is called the tail. Here's a couple of examples comparing vectors. You can see these two vectors are not the same. They are not equal because they are not the same size. These two vectors also are not equal. Even though they may be the same length, they're not the same because they're going in different directions. These two, on the other hand, are the same because they're both going in the same direction. They're parallel to each other. They are also both the same length, or they have the same magnitude. Here's an example of what we use vectors for. Vectors are just a way we express force. So this airplane, it has lift. That's one force acting on it. It has weight. That's another force acting on it. It has air resistance pulling it in that direction, but yet thrust is moving it in the third direction. This is also an example of Newton's third law. For every force, there's an equal and opposite force. For every action, there's an equal and opposite reaction on it. Okay, momentum is the quantity of motion, so we can determine the momentum, how much motion is taking place with this boat by multiplying its mass times its. You can see from these two diagrams, or hopefully you can, momentum, remember, is mass times velocity. So it is directly related. It's a direct proportion or direct relationship between mass and velocity. As velocity increases, so does momentum. As momentum increases, so does mass. So they are directly related. This would be an example of a closed system. You're in the laboratory, we can shut out everything from the outside and prevent it from getting inside. That makes that a closed system. Here's another example of a closed system. everything that's going on inside here, nothing from the outside is getting in. Here's an example of angular momentum or rotational momentum. You have an axis of symmetry about which this thing rotates, and that makes it and that means it possesses angular or rotational momentum. Here's another example. The football can has an axis of rotation or axis of symmetry here, so it can spin that way, or you could spin it this way as well. There's another example. The angular momentum will increase as she brings her arms in because her axis of symmetry is better, and when you bring those arms in, it creates that tighter axis of symmetry, so she's going to spin a whole lot faster. Collisions. This would be an elastic collision. The ball is going to hit the pins. The pins will absorb that kinetic energy from the ball and will move. Here's an example. Here's the cue ball. It's going to be hit with the pin, and then it's going to in turn cause these other balls to move. That is elastic. An angular collision would be here. Like if the ball is going to hit these at an angle, it's going to cause these to go off in all kinds of different directions, not just a straight line. Here are some examples of inelastic collisions. You got the bug on your windshield. That's definitely. If you have any questions about these, please just let me know, and we'll talk about it again on Tuesday. Make sure you read your notes carefully. All right. Have a great day. See you on Tuesday. Sound and heat and destruction of her. Not necessarily the pole. The pole is the heavier object, and it's going to stay the same, whereas the lighter object will obtain most of the destruction there. Here's another example. Got two objects. Here it is. They are before collision. Here they are after collision. This is inelastic because they are stuck together, moving together in the same direction. If it was truly elastic, what you would have is you would have the balls hitting, and then the red ball would stop and the blue ball would keep going. So any energy that the red ball had is completely transferred to the blue ball. That does not happen in an inelastic collision. Energy is not conserved in an inelastic collision. It's lost to heat, sound, and destruction of shape.